The title of my dissertation is Infrastructures for Data Dissemination and In-Network Storage in Location-Unaware Wireless Sensor Networks. I am going to start by introducing the problems we consider here. And in this introductory part, I'm going to try to speak mostly in layman terms so that everybody gets an idea what's going on here. We first study event search and localization in location-unaware wireless sensor networks, where we have this network of location-unaware sensor nodes randomly scattered in a plane. We have uniformly distributed sources. We have a collector here that is interested in one particular source, in one particular event, but it's not aware of the position of the event of interest. In the existing research, flooding-based methods are prevalent, in that a query is sent to flood the network until it reaches the source of interest. And then usually one of the routes is endorsed, and that's the route that the collector uses to retrieve data. However, these approaches are very energy inefficient, and therefore we propose a scheme for data search based on forward progress dissemination protocol that propagates data along straight lines away from the source. We argue that advertising along source spokes, as we call those straight propagation lines, increases the likelihood of information discovery and, in addition, avoids some negative implications of flooding. Okay, now we introduce the mobile data collector that initiates the search from a random position by disseminating its query along the also straight propagation lines that now we refer to as sink spokes. And the intersection of sink and source spokes defines the search success. Okay? As new events occur in the network, an infrastructure of intersecting spokes is emerging. And now the source can utilize the existing infrastructure to advertise the new event, and it covers the network area better, increasing the likelihood of information discovery. Of course, when a new collector appears, like here, he is going to have a much easier and much more energy-efficient task to retrieve data. And in addition, location-aware collectors can assist localization of network events by using this infrastructure of intersecting. Now that gave us an idea that we can actually bootstrap an infrastructure of a certain shape, specifically a web-like infrastructure, by putting a preset node, a bootstrap node, in the center of the network and letting it propagate equidistant radial spokes all the way to the network perimeter, thus partitioning the network into those wedges and creating this backbone. Now, when a random source appears, it is also going to create those source spokes until they intersect with the backbones. Obviously, this infrastructure makes our search for data events and data retrieval much easier. But in addition, look what happens when a new source appears in the adjacent wedge. Those two pairs of transversal spokes can now associate based on a similar distance from the center of the network because they intersect in the same backbone spoke. And this association can go around the network until it closes in what we refer to as isometric network. The term transversal spokes here refers to spokes that are the shortest ones that intersect the backbones. Now, this system of isometric routes partitions the network into circular subnetworks, and of course we have the already mentioned backbones. The circular subnetwork is a network model that we are going to use in our further analysis of data collection, and more specifically, this circular network actually consists of relays around this isometric route and all the nodes in the transmission ranges of those relays. So we kind of have some squads of nodes around each relay, and we call it a circular squad network. So that's our basic model that we are going to use. Okay, now I finished with the first problem and gave a sketch of solutions. our second problem is data collection from the fingertips of a randomly positioned collector, where now this collector is interested in obtaining a snapshot of all data in the network. The same randomly deployed network, uniformly distributed sources, collector. Collector wants a snapshot of data and appears at a random position. Ideally wants everything in its vicinity and its fingertips, and most importantly, collection delay is limited. That's a key word here. We want minimum delay data collection. Now, if the collector uses some of the existing approaches to reach each of those sources in the network, it is going to take a lot of energy, and it is going to incur a large delay. Some of the existing approaches rely on encoded data storage, where the gist of this approach is to have those independent source packets uniformly mixed around the network so that they become available to each and every source, each and every node in the network, and the nodes can then make random linear combinations, thus providing basically a distributed code. That we want that code to have such properties that allow collector to gather data from its fingertips, from those closest nodes. So we need some kind of storage protocol that is going to control that. However, mixing data uniformly around the network incurs a high dissemination, high communication cost. As opposed to that, our approach relies on already introduced circular wireless sensor networks, where we look at a data collection as actually a sequence of collections from those circular networks. We have this scalable approach now, where now when the collector appears, it connects to such a circular or donut-shaped networks. Now we are in a donut mode. It collects to that network through the backbone to a relay that is called collection relay, and gets all the data of that collection relay. Okay, so this closes the introductory part. Here's, just to mention, here's our circular squad network that we are going to use for data collection. That's a description of how we collect from the vicinity, just to have that in mind. Okay, this is like a more formal talk outline. So we mentioned we need this forward progress protocol, but we have a location unaware network, and it is very difficult to come up with something that would control straight propagation of data in such a network. So we introduced a protocol dubbed Bespoken that enables straight line propagation. We give analysis and design guidelines. We then talk about an adaptive version of that protocol. And then in the second part, we talk about data collection with minimum delay. We talk about it in terms of dissemination requirements, encoded distributed storage, analysis of belief propagation decoding with a technique that we call doping, later introduced. And we finally end up with collection cost analysis. Here's a famous Bespoken protocol that organizes sequence of relays that steer data propagation along a straight line. Now I'm going to introduce spoke building, or how to follow a direction set by the first two retransmissions without an external geographic reference. We have those two subsequent relays, and these are our main characters, pivot and leading relay. The first pivot and first leading relay define the direction or axis of the spoke. And then the subsequent sequence of relays is selected by a protocol which attempts to follow the spoke axis. Now, this is the protocol engine. It is fairly simple, but it's not going to be simple to analyze it. So, okay, so just note that black dot always denotes the active node, that the red full line denotes the current transmission, and we're going to see green dashed line denotes previous transmission. Now, in the step one, the leading relay, node 1 here, sends request to send control package with the range, transmission range, capital R. In the second step, the pivot node 0 here is now active and sends a block-to-send control package with the same transmission range. This blocking package blocks all the nodes inside its transmission range from retransmitting data further, except for the node that sent request to send. Having been granted permission to retransmit, node 1 now sends a data packet of transmission range small r and becomes the new pivot. The data circle here and the block to send BTS circle form a crescent of area C2. This crescent contains candidates for the next relay. And now a random node from C2 declares itself the new leading relay by simply being the first one to send request to send. Now this repeats recursively. Okay, we have seen that spoke propagation is basically a sequence of data packet transmissions affected by the choice of protocol parameters small and capital R. And now we are going to determine required values for the protocol parameters in order to achieve a desired spoke behavior. And we express this desired behavior through two constraints. One is the outage constraint that is formalized as a probability that the spoke dies before reaching a distance d should be smaller or equal some small value epsilon, which practically means we wouldn't like the spoke to encounter an empty crescent before it reaches the distance d. The second constraint, the wobbliness constraint, is formalized as a requirement that the deviation of the current spoke direction be limited to the cone minus phi naught, phi naught, which practically means as you go along, your current direction should always be within the area of the attached cone. Okay, we find that those two constraints can be decoupled, and from now on we separately analyze. Now, in order to formalize the outage constraint, we have to introduce the hop length process. Notice that the hop length is basically just a distance between the previous relay and the new relay. And when it's the shortest possible, we can basically imagine that we attach a contracted spring coil to that hop length, which pulls the data circle inside this blocking circle and only exposes this tiny area where we hope to find the next relay. And of course, this is exactly the situation we would like to avoid, because this tiny area translates to very low chances that we can find the next relay. However, if we do find the relay in that small area, the next hop length is going to be longer, much longer. This is a comparison, and such a long hop length induces a very large crescent, so that our chances now to find the next relay are much higher. We refer to this property as spoke self-recovery property for obvious reasons, and also just observe that in this large crescent here, we can now make any kind of hop. We can make a short hop, we can find a relay that creates a long hop, anything in between. And to all those hop lengths, we associate crescent areas that are increasing functions of hop lengths. So we here have a one-to-one mapping. Now, an important observation. This is the protocol engine is simple, but the analysis is pretty difficult, and we need, for analytical tractability, we need to quantize the hop length process in order to get some closed form results. So because of the mentioned one-to-one mapping, instead of quantizing the hop lengths, we quantize the crescent areas. We decide how many states the associated Markov chain is going to be. For example, we are trying to minimize the quantization error, and based on that decide how many states we are going to have. Then we partition the crescent area into as many strips, and then the transition probability that we transition from state I to state J is equal to the ratio of the area of the strip associated with the jth hop and the crescent induced by the I hop. So the Markov chain is a hop length process. So basically, to each hop length, you associate a state in the Markov chain. And as many states as you get as you partition this crescent area, as the strips you partition this.
It's finite state because you cannot have.
Because it's very difficult to analyze it.
Why is it finite state? Basically, is it because
I quantize it.
That's fine. But it quantizes, it becomes discrete, but it cannot go. The hop length cannot.
Yeah. So the hop length can go only from capital R minus small r and to r. To small r. So because of the geometry of this. Because of the geometry. So the range is limited to capital R minus small r, from that to small r. Okay, so this results in this triangular transition probability matrix, and it's triangular for already introduced reasons. Remember, when we are in the shortest hop state, we can only transition to the longest hop state, and when we are in the longest hop state, we can transition everywhere. So just to mention, with quantization, this one-to-one mapping is preserved. Okay, now we talked about transition probabilities only in terms of the ratios of areas, and we disregarded the underlying spatial distribution of nodes, which is modeled as a Poisson point process of unit intensity. Now we have to superpose that to our model, and just to mention, for each hop, for the nth hop, the hop length induces a crescent that contains Zn nodes, and the conditional expectation of Zn is equal to the area of that crescent, given that we have a unit density of nodes. Now we are mostly now interested in the case when Zn is equal to 0, because that's when the outage happens. We define now a happy event when the spoke propagation continues for eta hops. We define the outage time as the minimum k for which zk is equal to 0. We next define a complementary event to happy event when the spoke stops prematurely or the outage time is smaller than desired eta. And then we can calculate the outage probability through the probability of the happy event. Here's our happy event. We basically just continue propagating for eta steps where each step induces a non-empty crescent. We call it a successful look ahead. And it consists basically, the probability of that successful look ahead consists of two parts. The first part is basically just probability of transitioning from hop I to hop J, described previously with Pij. And then, in addition, we have to make sure that the crescent induced by hop Hj, Cj is not empty, which is for Poisson point process equal 1 minus e to the power minus Cj, denoted Ej here. So we define this new transition probability matrix now, P tilde, and using that matrix we can easily calculate the probability of happy event. Just go eta minus 1 steps through that matrix, given that we started from some state n, and that state didn't have an empty crescent. Okay, now we model finally the outage constraint using a large R approximation, and this non-uniform quantization, two-state non-uniform quantization of the crescent. We then create the P tilde matrix for such two-state Markov chain, and we apply eigenvalue decomposition to that matrix. We find out that the probability of outage depends only on the largest eigenvalue, the dominant eigenvalue of the matrix. And by expressing this dominant eigenvalue in terms of C1 and C2, we obtain a closed form expression that relates the bound for the outage probability to the design parameters of the protocol. The dominant eigenvalue is basically the eigenvalue that describes the transient nature of this Markov process. basically you got to stop at some point. But given that you have the post-point distribution underlying, the second eigenvalue describes this self-recovery oscillatory property that basically, so this is kind of mean behavior. The largest eigenvalue describes the mean behavior, the transient behavior of the process.
And eigenvalues are for the stochastic matrix you have for the transition matrix? Is that you are taking the eigenvalues of what matrix?
The matrix with the look ahead. It's not a stochastic matrix.
Oh, okay.
It's not doubly stochastic, it should be one.
Yeah. And you don't have a trap state at all there, so neither I normalized it. Okay, so here's the outage probability, the graph of outage probability. This is simulations. This is analysis based on the matrix, taking the power of a matrix. And the green one is large R approximation. Of course, I took an R that actually satisfies the condition for large R approximation, which is a realistic R, by the way, so based on the network size. It is just taking this matrix to the power of eta minus 1. Just taking the power of the matrix.
The matrix derived from
the quantization.
The non-uniform two-crescent quantization.
Exactly.
Not the
Exactly. But no. Actually, this matrix is not two state. The analytical results based on the matrix does not involve a two-state Markov chain. It's many-state Markov chain. I don't recall right now how many.
Okay. So then the larger approximation is the larger approximation to the two-state concept.
To the two-state. Okay.
In the simulation model?
In the simulation model, I basically just I create a network of uniformly distributed nodes in MATLAB, and then I go hop by hop searching for the relays.
No quantization.
Her analysis has this.
It's just the real spoke propagation through a field.
I spent a lot of time simulating that.
Yeah, I have nice pictures. Roy actually suggested that I send my artistic work to some competition in Princeton based on my research.
I forgot that I made this. Yeah.
Okay, now in order to relate these values of design parameters to the wobbliness constraint, we introduced the angle process, where for each hop n+1 we have the instantaneous angular deviation denoted by phi n+1, which is practically just an incremental change in the direction of the spoke theta n, so that theta n+1 is equal to theta n plus phi n+1. However, these increments are not independent, and here is where the difficulty lies. So we now observe that the angle deviation sequence, phi n, is modulated by the previously introduced Markov chain of hop lengths. Observe here that when we make a hop, transition from state I, hop length I, to hop length J, this arc is defined whose subtending angle actually defines the support of the random variable describing this incremental angular deviation. So it's a uniform random variable with a support defined by the previous two hops. By the
uniform approximation, right? The crescent gets skinnier near the.
It's basically it's not an arc. It's a segment of an annulus of a tiny width. So,
the
but
uniform is approximating that kind of thinning annulus by a uniform.
yeah, but it's incremental though. Okay, now we have the angle or direction of the spoke defined as a partial sum of those conditionally independent angles. And we refer to that as Markov modulated random walk. We now study Markov modulated walk stopping time with respect to this threshold, phi naught, where the stopping time is defined as a minimum n for which the absolute value of the angle is larger or equal phi naught. Practically, it.
Is step by step, or is cumulative over the path?
Excuse me?
The angle.
The angle.
Is cumulative?
No. It's a fixed. It's this cone that I present. Sorry, actually, this is this cone that I presented at the beginning, and this is actually phi naught. So it is always associated. It is in the direction of the spoke axis defined by the first two transmissions, and it's always oriented in the direction. And then this is the current direction. So we are trying not to get out of this area.
The area is defined by the very first transmission.
Exactly. The direction is defined by the first transmission, and this is design parameter, how much we want to constrain the wobbliness. Okay, so this.
It was easier to analyze.
Yeah, so this T phi naught, the stopping time, models basically how far the spoke goes without going off course. However, it is extremely difficult to stochastically characterize this random variable, especially its PDF. So we resort to two constraints. One is constrained in the mean, where we require that the expected value of the stopping time is larger than some n, larger or equal. And the second one, in the second one, we are bounding the CDF of this stopping time random variable by using some large deviation theory. We use very elaborate mathematical methods to find the results here, and it results in those two sets of guidelines for the design parameters. In both graphs, we are orienting spokes, 500 spokes, in the same direction, going eastward. And in the mean design shows that we cannot control wobbliness quite well because the stopping time variable has a very large tail. However, when we apply the CDF bound based design, we control wobbliness much better, but at the expense of a somewhat increased outage probability. So we, in a way, we give guidelines to the designers. Depending on what their criteria is and the importance of their requirements, they can choose one or another. The most important thing is you are capable of going away from the source in a location-unaware network.
So I think, what is the design D here, or eta? I think that's what.
Excuse me?
What is the design D for eta? Is it it's somewhere at 100 or 150? How far you want it to go here?
Oh, D. I guess in order of 15 hops. Oh, D, number of hops is, eta is 15. This is 400.
I don't think you just let it go all the way, but you design.
No, my design is up to here probably. I guess it was 15 hops time about 20 meters of range, transmission range. That's the distance. That's approximate.
This long time ago.
Yeah.
So your design depends on the Poisson parameter number.
On the density of nodes.
So basically,
The network, the specific physical event that you're monitoring that is expressed in terms of density of sources needs to be well covered by the nodes. So that's the idea. If it's well covered, then you can create something that propagates fairly straight. So just to summarize this, our design was based on an observation that the hop lengths form a Markov process, that the spoke direction process is a Markov modulated random walk, that for simplicity reasons we need to quantize, and we need a proper non-uniform quantization that captures the property of this Markov process in order to obtain closed form expressions. And then for the wobbliness constraint, we studied the Markov modulated random walk associated with the angle process as a product for martingale in the transform domain. So we used this martingale mathematical models. We studied the generalized world identity for the stopping time. This is how we got our expected number of hops until we go off course. And we derived, for the CDF bound constraint, we derived generalized Chernoff bounds for the CDF of the Markov modulated random walk stopping time. finally, just to end this first part, I want to introduce the adaptive version of the Bespoken. This is the basic Bespoken enhanced with the mechanism we refer to as one-step backward repair protocol. The current leading relay, denoted here with CLR, is the guy who gets aware when the outage occurs by observing the absence of the RTS packet within some timeout. So having observed the outage, the current leading relay can solicit its peers to take over, to replace him in the role of the leading relay. So like one peer from the same crescent is now the leading relay, took over, and as a result of that, we have a new crescent that has a pretty large innovation area with respect to the empty crescent, and therefore the chances to find this next relay are much increased. And we can see the practical value of that. It's pretty simple, but the results are actually stunning. Here's a graph that represents the same spokes directed eastward. The black traces, where is it? Okay, the black traces here are the adaptive Bespoken traces. The red traces are basic Bespoken traces. We here have a network with a hole due to some hazardous event. And you can see that the adaptive Bespoken spokes manage to crawl along this hole, while the basic Bespoken spokes just immediately get stopped here. The second example shows a thin network. Basically, you design your parameters for a certain density of nodes. And then the density is decreased to half its initial value. And then you can see that the basic Bespoken doesn't cope well with that change of the density. It's not quite adaptive. Well, the adaptive one obviously manages continue propagation of spokes. That ends the first part. Okay.
So the red is basic. Like those spokes, and those are short.
The reds are basic, yeah. Yeah, okay, so.
I think the color scheme is wrong. It might be the new, better thing should be the red more specific.
Can you tell us a little bit of how these results would apply to different propagation environments?
For those two, the last ones?
Yeah, the angle bounds that you computed and the outage probabilities. How do I apply them to a real system if I deploy it?
Okay. So for the real system, for example, you have, like, let's take a landmine field. You want to detect landmines somewhere. You don't want to enter the area of the network. So the only way to approach the network is to sit somewhere at the perimeter of the network and to basically probe the network. So your sole requirement is to get out of the network, to hit the parameter of the network, not the, the wobbliness. Well, when you're creating an infrastructure of intersecting spokes, then you would like a certain direction constraint, higher direction constraint, where you can then use that directionality to locate emerging events or to, come up from with some balancing, routing schemes or whatever.
Well, that's fine. My question is, if you do that, you will not have a unit disk propagation model. You will have some probably log normal shadowing model.
Oh, the shadowing model. As to propagation models.
Constraints or results tell me anything.
Yeah. Okay. So that's a very complicated question. Our assumption is that it's an isotropic propagation. I did start the research on shadow fading. I consulted some big experts on that, but nobody actually knows how to correlate the blueprint of a range to shadow fading power attenuation. So whether it has an amoeboidal shape, whether it has pseudopods of what size, and nobody knows. But our research, I started this research concentrated on the fact that, can I just draw something here? Okay, so you have basically this kind of geometry. Okay, this is your R, and this is your R. Now we already traversed that part, which means that this part is good. You didn't have shadow fading on that part. The only thing you have to make sure is that you don't have shadowing here. And this shadowing is basically most of the models that account for spatial correlation due to shadowing are looking at the boundaries, and this is what interests us. And our crescent is at the end of this boundary, and most of the nodes along this direction basically kind of have a similar history of encountering obstacles. You know, so that if you have this with the big R, you're going to have this with the small r as well. You know, because you had somewhat similar history of encountering obstacles. But to actually correlate that, it's not easy. So I used some Brownian motion-based model of shadowing, and there's some research-based, and actually quite nice pictures that speak in support of our protocol. But it's not conclusive, and this is basically future work. So
there's no simple relation. You can say your computer is on upper or lower bound.
no, I haven't worked on that. Okay. Does this work? Yeah.
You know, within the crescent, if you just say, oh, who's in the crescent, like, oh, with shadow fading, it's a kind of a, you'll still have a Poisson number, but if
Shadow fading, you don't get a crescent. Right?
But you don't get a crescent,
You
so
might
now
even be
this,
going backwards in your communication.
But I think her point is that because of this radial kind of, but you can, one of the models that we had was along a radial line coming from your transmitter. You essentially have maybe some sort of absorption process. You know, the front nodes see the same blockage as the back nodes, sort of like. So you can maybe model it as some sort of decay along the line. That sort of property helps you in this kind of.
But it's
But you could only do simulations, maybe. I don't know.
But that's something, it's not easy at all.
You've done the simulation, though, right? It says, oh, it might be worth just throwing it in as a kind of experimental.
Yeah, but I guess with a network that has a certain geometric structure, like let me just show you quickly. I'm just going a little bit ahead of jumping ahead.
The reality in some of what has been done here is that.
Okay, so this would interest you. So if you have a network that is, for example, a vehicular network, and you have some geometric structure around it, then it's much easier to propagate along the straight line. You have high density of nodes here along that network. It's a closed isometric network as we modeled it. And then, you know, if the road is bent, you can apply the adaptive version of the protocol to kind of go back in reverse and then straighten up. And with that, I guess, my guess is just it's a conjecture that it would be a much better performance, and you wouldn't have to create this tiny crescent of a small width, because the geometry of the network is helping you a lot. And you can correct yourself. Yeah, they're on the road. Well, the mobile collector doesn't have to be here. It can be a person with a cell phone in a car, you know, when you're collecting data.
In this kind of environment, you use a different solution, right?
I guess.
Where you would tag the nodes with some kind of like, I'm on I-287 as a tag, right? But then implementing protocols by communicating among nodes with certain tags would create the same infrastructure you're creating this other way, or maybe, you know.
Yeah, okay.
You're saying it's location, not location on the map, it's location on the map?
Yeah, I think the fact is, if you deploy a network on the roads, right, you would somehow embed the awareness of I'm a node on 287 or I'm a node on Route 18.
What if it is mobile?
Right, just with GPS information, and that you can look up from the navigator.
Or even not just on the navigator, but we can embed that in the
You can,
sensor
if
node.
you want to,
If you make the encoding nodes in the road results rather than in the road range.
Yeah.
Even if you know the location, or at least partial location information, you run into similar problems.
Thank you comes much later. Okay, so we are back here. So, I mean, it's a model. So, okay, so now we talk about data collection with minimum delay from wireless sensor network. Just a wrap up. We rely on this protocol to make those building blocks. Here's a simulation result. Building blocks that make possible such an infrastructure of isometric routes and backbones that we model as a system of concentric donut-shaped networks, or more precisely circular spot networks. And now we are going to use that approach because it's simple and it gets some closed form results where we consider in particular dissemination, coding for distributed data storage, and decoding strategies for data collection. Here is how the coding applies to data collection in such a network. We have the same randomly distributed nodes. We have uniform sources. We have this mobile collector approaching the network in the vicinity of those 4 storage nodes. We mentioned that there's this uniform mixing of independent source packets requirement, and as a result of that, this is previous work, by the way, just explaining the phenomenon. And as a result of mixing, the source packets of source 1 end up in storage nodes A and C, source packets of source 2 end up in A and B, source packets of source 3 end up in C and D. And then the storage nodes combine those independent packets into linear combinations with those random coefficients, and this is the matrix equation that describes those linear combinations. Now what happens when the collector only gathers data from the first 3 nodes, like this? Is he capable of recovering the original data? The answer is affirmative. Oops, sorry. If the associated matrix G is a full rank, or that is, those linear combinations are independent. The independent linear combinations in this particular setup are usually achieved by letting each packet replica traverse the graph associated with a network sufficiently long before being stored at a node. And usually we model a wireless sensor network by a random geometric graph, like this one here. And for random geometric graph, sufficiently long is of order n. This is how it works in practice. So this is our source node 1. We take its packet, we create a header, we put a counter in the header, initialized to n, and we let the packet traverse the network, hop from node to node. Each time it hops, it decrements the counter. When the counter reaches 0, it gets stored at node A. The same with the second replica of the same packet. After approximately n hops, it gets stored at node C. This is basically the same random sampling of a large state space, like a Monte Carlo method, where you would like to achieve, to get some empirical results based on some stationary distribution, empirical sampling. So, however, this is extremely costly. The communication cost is prohibitive, order of n squared for this random geometric graph. And in addition, random geometric graph doesn't properly model wireless sensor network because it doesn't model the fact that at the same time, each node in such a graph has active all the adjacent edges, which we refer frequently to as multicast this advantage. As opposed to that, our approach is infrastructure-based. It offers solutions for dissemination, where this solution exploits the symmetry of this circular network, distributed data storage that exploits the wireless multicast advantage, and the data collection and recovery, which exploits the property of the decoding algorithm. The assumption here is that mobile data collector will establish connection with a random collection relay, so either here or here. The goal is to increase storage capacity of the nodes around few relays adjacent to the collection relay, like here, so that all data of the asymmetric network is available in the vicinity of the selected relay, and to provide minimum delay collection strategy that assists delay propagation decoder. Finally, the focus here is comparative collection delay analysis for this circular network under proposed strategy and some other approaches, common approaches. Here is a close-up of our circular squad network. This is how our dissemination works. We have end relays. We have, within the transmission of each relay, we have some other nodes. We have some of those nodes as sources, and those sources associate with the closest relays, making relays basically virtual sources. So we have n virtual sources here if we have one source per relay. So we have n packets to distribute. Relays disseminate or mix data, and we here consider two dissemination methods. The plain relaying, where each relay just sends its own packet or forwards each received packet until everybody gets everything. And the degree 2 combining, which we propose, where it is basically a simple flavor of network coding based on wireless multicast advantage. Here, n is equal 7. These are our relays. We are going to observe behavior of node 1, relay 1, and what's going on in its buffer, what is the content of its buffer as we go through dissemination rounds. At the beginning of the dissemination process, each relay has its own data, its own packet. So the node 1 sends its packet P1 to the neighboring nodes, and the same happens with the node on the left and the node on the right. And then the node 1 is having received P2 and P7 is capable of making the linear combinations of P2 and P7, thus simultaneously sending an innovative content to both left and right neighbor. The same happens on left and right side, and having decoded P6 from these linear combinations, it has P1, so it's easy to decode. In the next dissemination round, node 1 sends P3 plus 6, again sending innovative content for both neighbors. So that decreases the number of hops by 2 with respect to non-combining. Just to mention, there's a similar protocol in the reference paper here. So this basically our dissemination uses the symmetry, radial symmetry of our network. Now this is storage. We defined a storage squad as a set of nodes in the range of relay. The size is h, and given the density of nodes lambda, we have that h is equal lambda r squared. We already fixed number of sources to 1, and this defines the so-called coverage redundancy factor, which is equal to the ratio of those two densities. This basically corresponds to what I already said. You need to cover your physical phenomenon well in order to report the events. This is another model of the same thing, of the squad. These green guys, the green nodes, are capable of overhearing transmissions from both relays. And here is how the storage squad dynamics. The relays disseminate data. This is the transmitter of this relay 1. It sends data. Transmission is overheard by both left and right neighbor, and at the same time, it is overheard by all the nodes in between. Those nodes overhear and store data, and they may combine new packets with already stored ones. So they utilize this, leverage this multicast wireless advantage. So storage is only as important as it helps us with collection process, and here we are describing the interplay of storage and collection methods. We have number of sources or relays n that is much larger than the squad size h. We have each squad node having a unit buffer, which means if a storage node only memorizes this one packet, the collector is not going to be able to gather all the data from only one squad. So we need some kind of better packing of the data, and that packing is basically achieved by coding. So we are going to come up with a storage method that packs information needed to recover data in the smallest number of adjacent squads and to provide diversity needed for this randomness of the collection location. And so we define the super squad as a collection entities composed of set of adjacent storage squads. The size depends on the storage and collection method. For example, for coupon collector, that is a common method in the theory, where each node randomly decides ahead of time which one out of n package to store. We know that by the coupon collection model, we need n log n packets, and so the super squad size is n log n over h. We define collection cost per source packet for such a collection from super squad, and obviously it depends on the super squad size. While just to juxtapose this to the collection cost when we are polling data from the original sources, it doesn't depend. It only depends on the number of relays in the network. So we are now infusing some different structure in the network based on super squads. Here's finally our approach. Okay, so we are coding around this network. We are overhearing and making linear combinations. We have a large number of sources, so our code needs to have property that allow for linear decoding complexity. We want to minimize delay, and that includes decoding. Okay, so this is the matrix, random matrix that represents this coding process. We have n sources represented by rows. We have hn storage nodes around here that each contain one linear combination represented by the column. Non-zero elements here are the source nodes included in the linear combination, and we refer to the number of those non-zero elements as a degree of the combination. This is all controlled by our storage protocol, and we want the statistics of those degree combinations to satisfy the requirements for decentralized counting code, because then we have linear complexity of decoding. Here is how we connect in order to get data. This is our random collection relay. We get data from this part. This is our super squad. And super squad is modeled by this random submatrix here. So the main question is this matrix invertible? Does it have a sufficient number of independent linear combinations? We can make sure that we have sufficient number of linear independent combinations by taking much more than we need, a thick super squad matrix, but then that incurs a very large collection delay, and therefore we resort to a trade-off in collection strategy. We have upfront collection from a small super squad, small number of KS code symbols, and we have on-demand decoding. So we start on-demand collecting. We start decoding from this super squad. When our decoder gets stuck, we want help, we go and demand another symbol that is going to continue our decoding process. And we argue that this number of symbols collected totally, upfront collected and on-demand symbols are sufficient for decoding all packets. Some of those pairs are feasible number. This is the model of our upfront collection. We have n sources. We randomly combine them into collected KS symbols. Each of the KS symbols is represented by the column, as I already said. The rows correspond to sources. You see that source 1 ended up randomly into nodes 2, storage nodes 2, 5, and I, like here in this row. This basically represents any decentralized erasure codes. But for us, we want to control the degree distribution of the column degrees, and in order to obtain the decentralized counting code. The payoff, as I said, is just the linear complexity of decoding. This is now the system model for decoding. Our storage node combined packets into linear combinations, making counting code symbols. The code symbol degrees follow ideal soliton distribution, so this is our starting assumption. How we achieve that? Basically, each node samples the number d from ideal soliton distribution from 1 to n. Then, for example, if d is 3, then I go and I sample 3 numbers from 1 to n. And then I know, for example, number 2, number 5, and number 17 are going to packets that I'm going to store as I'm overhearing them. So this is how we empirically get the distribution. Then the sink collects a random set of KS code symbols, where we, for simplicity, take it to be n in order to obtain a square matrix. And this defines the columns of this generator matrix. Now we start the belief propagation decoding if and only if this matrix contains a degree 1 column. And here's how it works. So this is our starting matrix. Let's identify a degree 1 column. This basically reveals one source symbol here that effectively erases one column. The erasure, one row. The erasure of that row may create new symbols of degree 1, like here, that in turn erases another row, and each single decoding round effectively erases one row, making this initial matrix, causing this initial matrix to shrink. And so if we start it from S naught, which is of size n by n, after L rounds, we end up with SL, which is of size n minus L by n minus L. Now, we want, it is absolutely the most important thing to have degree 1 columns that form the ripple, because ripple is what we know and we use to learn what we don't know by peeling or erasing those layers from higher degree symbols. And so as long as we have degree 1 symbols, we are continuing, but then at some point we may get stuck. And then the question is, can we continue? Yes, we can. The only thing is that we are trying to identify here degree 2 columns. Then we take one of the source elements contributing to degree 2 column, we bring it in, we erase the corresponding row, and we create a new degree 1 symbol. And then we can continue, we are unstuck. This method is referred to as doping. Okay, so we now characterize the decoding round. We have column degree AN minus L, which represents the number of non-zeros in a random column of SL. The column degree evolution shows us how the statistics of this number change with L. And we are going to use we are going to analyze that evolution in order to come up with a number of dopings that we are going to need. We are particularly interested in ripple evolution. Here's how the ripple behaves with the decoding rounds. We see that at times the ripple hits 0, and these are the times when we need to dope. We define a random variable y here as interdoping yield, and this is exactly the number of decoded symbols between dopings. Now, if we are capable of calculating the expected value of that random variable, then we can use walled identity to calculate the number of doping symbols. And then we can include that into our total delay cost. Start with ideal soliton distribution. As I said, this is the distribution. Just observe that for D equal 2, this is 1/2. This is the shape of the initial distribution. This is ideal soliton. The most important thing here is that after L decoding rounds, the support of this distribution changes, of course, to a set from 1 to n minus L because we decoded L. But the shape remains the same. And that ergodic property of the initial distribution allows us to have a pretty elegant analysis and to obtain some closed forms. So the distribution change for D equal, the distribution shape doesn't change for D larger than 1. And now we only have to see what happens to the ripple, because ripple is the most important. And let's see. So ripple is the, just to remind you, ripple is the guy that allows us to take known input symbols in the degree 2 symbols and peel them out. So we do that layer by taking layer by layer of coding symbols and their degrees and peel them. Peeled degree 2 symbols become ripple, as we have seen in our matrix representations, and that's why our focus is on degree 2 symbols. Here's the matrix again. Now just look at the columns of degree 2. The expected number of degree 2 columns is n minus L times the ideal soliton probability for 2, which is 1/2. And we can look at those n minus L over 2 columns, in average, as independent Bernoulli experiments, where the success of Bernoulli experiment is 2 over n minus L. This P is actually the probability that our randomly brought source symbol or symbol taken from the ripple is going to hit a degree 2 column and peel it out. So as a result of that, our ripple increment is a binomial random variable with those parameters, and it remains, the statistic description remains the same for doping as well as decoding. We can, for large n, we can approximate it with a Poisson distribution of intensity 1, and we can conclude that ripple increments create a sequence of IID random variables due to ergodic behavior of ideal soliton. So, you know, our stochastic description is the same regardless of the doping round. This is a formal description of the ripple size, just relating the ripple size to the matrix at decoding round L. We are interested in stalled decoding event when the ripple is equal 0. The question is, what's the probability of stalled event? We know that the ripple is a partial sum of already described ripple increments, Ri, and then we just subtract n, because every time we have to take one symbol from the ripple. We analyze that using random walk. We associate a state in this Markov chain to every possible value of the ripple, defining the trap state as the situation when the ripple hits 0. We define at the same time as we used previously the probability that the random walk is in the trap state at time t, as just taking this power of the presented matrix. And then our probability that we hit ripple exactly at time t is just a difference between those differently parameterized expressions. Now, probability that the ripple is 0 at time t plus 1 is equal to the probability that interdoping yield is equal to t plus 1. So we had t plus 1 decodings in between two dopings. And this is represented by this closed form expression, also thanks to the great property of ideal soliton, where we obtain this Poisson distribution for the ripple increments, and then if you convolute Poisson distribution s times, you're getting another Poisson distribution just with a change multiplied intensity. So this is actually a great property that allows us. This convolution is obtained by observing certain properties of the matrix. It was an almost Toplitz's matrix. Look here, Toplitz's matrix, almost circulant matrix if you do some corrections. And then when you apply power, this is sort of a convolution, and we got the results in the closed form. Now, based on that, calculate the expected value of interdoping yield, and using our Helpful-Wald identity, we obtain number of dopings. These are the results. We define doping cost as the overhead of number of upfront collected, number of doped symbols with respect to the number of original source symbols. And we show here how this doping cost depends on the choice of the initial distribution. Here's our nice ideal soliton distribution. This is commonly used, famous robust soliton that is used in Luby's codes, in fountain codes. But in this case, this works better, gives us better, smaller doping cost, and the variance is much smaller.
So what does that axis mean, the y-axis?
This is percentage of what's the overhead, how much more with respect to the number of sources we need to bring in order to decode, how thick our matrix basically needs to be. Remember, with Luby gives k plus square root of k log square k over epsilon in order to decode k minus epsilon. So for certain values of k, that is a lot. And And so this basically is that overhead normalized.
So this overhead is measured. How is the overhead defined?
Overhead is what you collected, what decoder collected, minus
Those are the additional bits that you
additional symbols, yeah. Packet.
also account for communications overhead. Is that important measure?
That's basically these are hops.
All
No, later on when I do my collection cost, then I calculate hops. Now this is just the number of symbols, and then you relate that to the number of hops in the squad or differently.
She says 2%, but you have 1,000 symbols packets encoded, then you need to try to get 1,020 packets.
So that
Okay, so the next thing is how the doping mechanism affects this doping cost or overhead. This is our smart packet pool based on degree 2 symbols. And this is just randomly taking a source symbol to dope the packet, like blindly. This is the overhead gain, just comparing LT codes, Luby codes that are based on robust soliton and our approach. This is a simulated LT code. This is the bound that Luby gave in his seminal paper. This is our simulation results, and this just tightly connected black line is our random walk base bound analytical formula. So okay, so this is finally
Hold on, what is right above your random walk bound?
here.
You said that
Oh, this is simulated, our thing simulated. These are the collection cost curves. So remember this H, coverage redundancy factor, shows basically how appropriately you cover your events of interest. And they define the size of a squad. So for two different values, you can see that the optimum value of the overhead in terms of upfront collected symbols is at different points, but it's still very close to 1. So you only need to approximately stick with our square matrix. You have to approximately upfront collect n symbols, start decoding, and then dope when you need, which is of order of 2%. And here is a comparison of the collection cost, which includes hops and hop is of cost 1. 1 hop is that we normalize. This is normalized with respect to polling. Polling is when we go to the original source and take the packet off the source. This is the coupon collector. This is now robust soliton, and this is our approach, ideal soliton with doping. You see, this is the x-axis is 1 over h. So when h, the squad size, is very large, like 10 to the power of 3, then it makes sense to get everything from one squad, and that everything would be sufficient to satisfy the requirements of LT codes of robust soliton. So you don't have to apply any doping or anything. Everything is 1 hop away. When h is smaller, which are pretty realistic values, then you have your information spread around the network. You need to make hops, and then our doping approach makes sense. And it certainly makes sense better than coupon collected. There is like an in-the-mean approach, expected value, and polling. For a large network, I have to stress here, we have a asymptotically large network.
So the left-hand side of the right-hand graph is the situation like 10 to the minus 3, where 1 in 1,000 nodes is a source of data. Or is it
Exactly. 1 in 1,000 nodes is a source of data. So the redundancy is huge right there around him. That is assuming that we already fixed the density of sources. We have 1 source per squad. So H here is the local number of guys that are covering you. So basically, repetition code would suffice, I guess.
So how big is the squad in relation to H then?
It's H.
It is H. So then a squad around someone has 1,000 nodes. So then is like somehow physically something is not being accounted for. Like if the density of nodes over space is constant, then somehow if you have 1,000 nodes in a squad, then that circle's very.
Well, as I said, these are realistic things. These are not, and this shows where. This is not realistic, as you said. Then something is wrong. You have 1,000 nodes in a, basically it's probably some Eagles game where everybody is having a transmitter.
Yeah, but I think that's quite realistic.
But okay.
There's 68,000 people in the stadium at a spacing of approximately 1 per half square meter, and they all have an opinion about the game.
But they all have opinion, which means that the ratio between sources and storage nodes is not.
So we're over here, right?
We are here.
Okay. So how did you define these per collection costs in the left-hand graph?
Here?
Yeah. Did you explain that? Like what physically?
So.
Like there's you're assigning unit cost to certain things.
Unit cost.
So
okay, so I have to write this down. So it's easier than to. Oh yeah, I'm holding this. So the total cost is Ks times Cs plus Kd times Cd. CD is collection cost per doping, which for a network of size n, if you are here, your average is n over 4. Okay? For a squad size of S, okay, you are here, this is S minus 1 over 4, its average value, hops.
So it's essentially there's a unit cost of 1 per hop per transmission, and that you're calculating some number of transmissions that you need to.
Number of transmissions. So number of packets times number of hops. Every hop is 1 energy unit, 1 delay unit.
Does anybody else want to pursue this? So like 12 is physically is what? 12 versus 16. So like okay, so H is 15, right? Which is the squad is 15 members.
I have to admit that I don't recall the actual numbers here. I know this is 2,000, N is 2,000, but for this one, I have to look at my MATLAB.
But we can assume some numbers, right? I mean, if you want to give me an example to.
So no, I'm just trying to relate. So is it the fact that like, so why is it that, for instance, that?
So why is this higher? Why is this higher?
Why is the H equals 10 case? Right?
Because your length, your one-dimensional length dimension of your super squad is then longer because you don't have such a dense packing. So you have to hop more. You have to hop more. Oops. Okay. Oh. Well, that's my clicker. Yeah. That's.
The clicker is very powerful. So
I'm not used to it.
So you have to go. Like you still have. It isn't the next slide, is it?
No. Okay. No. Yeah, that's the next slide.
She was at 28, right?
Yeah, I was here, and this is my elephant page. You, sir.